you can represent in Hoare logic or in separation logic other relations between the precondition and the postcondition. But when possible, it's convenient and a good idea to do it this way. Why? Well, this function in Coq is total and deterministic. So it completely characterizes sort of the abstract view of what the C program is doing. It proves already that the C program is not non-deterministic in any important way. Well, it may be non-deterministic in that when it calls malloc, it could put this thing at a different place, but that's a non-determinism that's not going to be visible to the consumer of search trees, right? So this is a very good way to get the right level of abstraction for what your C programs are doing. Some C programs are intended to be non-deterministic in a way visible to the client. And when that's the case, you can't use this method. You can still represent whatever relation you like in separation logic, in Hoare logic. And in fact, that's what you will have to do. But when you can do it this way, it's very good. And the reason is, it allows this separation, right? The proof that your binary search trees, raise your hand if you did this proof. Okay, when you did this proof, did you realize that you were proving the properties of a C program? Okay, that the proof you did is exactly pluggable into an engineering solution where a C program has its properties proved. It's the other engineer who is doing the verifiable C proof that relates the C program to the functional program. So you get this modularity of proof that works very well. Now, let me come back to here. And talk about another example of this modularity of proof. This is a proof we did, looks like 3 or 4 years ago. Leonard Beringer, you know. Adam Petcher was then finishing his PhD at Harvard, and he designed and implemented this foundational cryptography framework in which you can do proofs about cryptographic primitives and cryptographic protocols. And the security properties you want to prove about a cryptographic primitive, let's say cryptographic message authentication, are that the adversary has a tiny chance of guessing the cryptographic function, right? If I'm doing a hash-based message authentication code, so I take a secret session key and my data, and I mix them together to get a hash code, and that proves that whoever claims something about this data had the session key, so it must be me. And we want the adversary not to be able to guess the hash value that goes with this source record. More generally, we want to say the hash function is a pseudo-random function, right? That a computationally limited adversary, let's say an adversary who can do no more than 2 to the 100 computations, has a chance of finding a collision no better than 2 to the minus 70. That's pretty good. That's the kind of thing you want to prove. So to do that proof, you work in the computational monad of probability spaces. And that's what the foundational cryptography framework is for. It's just a library in Coq. So the entire proof of cryptographic security of some pure functional specification of the hashing algorithm is done in the foundational cryptography framework. And someone else, namely Leonard and I, did proofs about the C programs in SHA and HMAC to prove that they implement a functional specification. And unfortunately, the functional specification that we proved they implement was different in some ways from the functional specification that Adam Petcher proved the properties of. So we got an undergraduate, Catherine Yee, to prove in Coq the equivalence of those two functional specifications. All right, so we have this proof, okay? The C programs that you find in OpenSSL that implement SHA and HMAC correctly implement the FIPS standards, FIPS 180 and FIPS 198, as defined by the National Institute of Standards and Technology. So we transcribe these two functional specs from their native language, which is LaTeX, right, a mixture of math and English, into Coq, all right? And you can inspect the Coq functions and compare them to what's written in math in the documents, and you'll probably believe it. Okay, then we write an API spec for SHA and HMAC, and I've showed you these API specs. They're how you lay out in separation logic the description of the data structures, how the data structures represent the things that the pure functions are talking about. Then we prove that the C programs in OpenSSL, SHA, and HMAC correctly implement the functional specifications. That's the refinement proof. Then we have a proof that the assembly language that comes out of the CompCert verified optimizing C compiler has the same observable behavior as these C programs. So that's the CompCert correctness proof. And we have, to prove the relation to the separation logic spec, we have our verifiable C program logic soundness proof. Okay. Well, the LaTeX version of the proof that HMAC is a pseudo-random function is well known in the literature for 20 years. But, you know, do you believe proofs in LaTeX? There was the 1996 proof, and Bellare 10 years later said, here's my new improved proof. So it's not exactly that there was a bug in the previous proof, it's just, but why would it need to be improved? We can be suspicious. Well, actually what Adam Petcher implemented in Coq was actually closer to the 1996 proof than the 2006 proof. Both proofs seem to be okay. We know that now because they've been proved in Coq. Okay, and so meanwhile, these depend on the cryptographic security of the SHA hashing function. Well, nobody knows how to prove things like that. All we know about SHA-256 is it shuffles up the bits pretty good, right? In a way that people trust as much as they trust any of those things, and it's probably good enough. And you know, if you have a better one that you can prove something about, great. So this is a very standard cryptographic assumption in the literature, and we have to assume it too. We write, you know, this as a hypothesis of the main theorem. But other than that assumption, the main theorem is that these assembly language programs correctly implement the standard, which does give the cryptographic security property. And the key thing is to separate the reasoning in the mathematics of the application domain from the reasoning about C programs. We were very impressed that Adam Petcher could do those scary-looking proofs about the computational monad of probability spaces. Adam Petcher was very impressed that we could do those scary-looking proofs about C programs. Okay? Each one, you know, requires a good deal of sort of training and practice to get up to speed in. So those of you that were here last week for the Verifiable C Hackathon had 3 days of that, and you got this far. And I think in a month you'd be pretty good Verifiable C engineers, able to tackle anything. But it still takes training and expertise. And you don't want to have the same engineer who also knows how to reason about crypto properties in probability spaces. Okay. So, now let me change the subject to something much more mundane. I want to talk about integers. So just a little interlude about integers. And this is mostly for the Coq novices in the room, the people that were last week in the Coq Intensive, where everyone got to play with natural numbers. And natural numbers are very nice. If they didn't exist already, they would have to be constructed, of course. But they have some unfortunate properties. And here's one of them. Theorem. It is not the case that a minus b plus b equals a. Right? And how do we prove that? Well, a minus b plus b equals a. We assume that for all a and b. We specialize h to 0 and 1. So now 0 minus 1 plus 1. But remember that the minus in natural numbers is what I call bogus subtraction. That if you subtract down below 0, it has to be a total function that has a codomain that's the natural numbers. You've got to put something there. You put a 0 maybe, arbitrarily. So if we simplify that, it becomes 0 plus 1. And so now we've got above the line 1 equals 0, and we can prove this by inversion. Okay. Coq has an integer type, z. And this represents the integers with negative numbers as well. And it is the case that a minus b plus b equals a. And we can prove that by omega. All right, so how do we use the integers? Let's look at what z is. All right? Z is an inductive type. Either it's 0 or it's a positive number where z pos carries a positive number, or z neg carries a positive number. And let's look at positive. A positive number is either 1 or it's 2n for some other positive number, or it's 2n plus 1 for some other positive number. Now, all you see is these weird constructor names. Where's the 2n and the 2n plus 1? And the point is that these represent 2n and 2n plus 1. And it's the interpretation when we write the add function and the multiply function on these positive numbers, we will write them as if that's what the constructors represent. This is a binary representation, unlike nat with s and o, which is unary. To represent a number, order of magnitude 2 to the n, takes about n of these constructors. So logarithmic in the size of the number represented, and the add function and the multiplication function also take logarithmic time. So you can actually do, even though Coq has no primitive representation of numbers, it's just the calculus of inductive constructions. So all you get is inductive data types. But you can do computations on arbitrary precision positive numbers in log space and log time. It works pretty well. It's a log n slowdown compared to your fixed point, your machine integers that put 64 bits all into the same word. And then similarly, the native arithmetic on z, which is either 0 or z positive or z negative of positive, takes log space and log time. Question?
Is arithmetic on z optimized?
Is arithmetic on z optimized? Well, what do you mean by optimized? It takes log time. That's pretty good. Now, is there an optimizing compiler? Well, yes and no. So there is a thing called native compute, right? If you take a Coq expression and say native compute, it will dump it into what's, I think, basically the back end of the OCaml compiler, and it will do what it does, which might include optimization. So that's fine. But let's just think about this as a logic. Is it even realistic to write a large, useful program where you just use these integers in that representation and don't even give any fancy extraction directives to try and hack them to use machine integers? And the answer is yes. The CompCert optimizing C compiler is extracted that way, just using this mathematical representation. Well, that works pretty well for CompCert because actually optimizing compilers don't use numbers that much. They use data flow analysis and symbolic things and register numbers which go all the way up to 30. And if all you have to compete with is the speed of GCC, then you don't have to work too hard either, right? If you have to compete with the output quality of GCC, that's hard. But the speed of compilation, no problem. All right. But on the other hand, there's a static analyzer for C, built sort of also on the CompCert operational semantic infrastructure called Verasco. Verasco is written in Galena and extracted to OCaml. And static analyzers do use a lot of integer arithmetic because the programs that they're symbolically evaluating have a lot of integers. So the Verasco team found that they did need to somehow extract to machine integers. All right, so the main point is Coq has the integers. And now that I've told you how they're constructed, you should forget it. You should treat them as the mathematical integers, which is an abstraction, right? Which has an interface, has operators add and subtract and multiply and divide. It has the theory of how those operators interact. And you should almost never do induction directly on the representation of integers, and rarely on the representation of positives. Yes?
I had a related question. So if we can define integers using this kind of binary defined structure, can't we do the same for natural numbers and that would be faster?
Couldn't we define natural numbers with some sort of binary representation just like the integers? Well, there is a thing called capital N in the Coq library, which is, well, it's either 0 or it's a positive number. So yeah, you can do that. I tend not to use N very much because N still has the problem of subtraction, right? So we're going to use the integers. The integers have a thing called 0, and they have add and subtract and successor and all the mathematical operators you expect. Use those operators, treat it abstractly. Don't unfold Z very often to its constructors. And now let's write a function that makes a list of the numbers 5, 4, 3, 2, 1. Okay, so it's a decreasing sequence of numbers starting at n. And let's do it this way, right? Decreasing z of n is, well, if n is successor of n prime, then n cons decreasing z of n prime. And if n is 0, return nil. So very good. The command has failed with the message unknown constructor z.suck. But z.suck is there. Right? It's a function from z to z. So what's the problem? Well, it's a function. It's not a constructor. You can't invert it. You can't match on it. So we could try again. We could say, all right, instead of match n, let's say if n is greater than 0, do n cons decreasing z of n minus 1, else if n is 0, then nil. You could do that. But that would not be structurally recursive, right? That a fixed point, all the recursive calls to the fixed point have to be on an exact substructure of the original thing. And n minus 1 is not a substructure of n. Okay. So, what could we do? Well, if we want to define this as a fixed point, we could define it